Okay, I'm a punctual person, so we're going to get started. And again, I'll let some people get in. So how this is going to work today, we have everybody muted just so we don't get a lot of background noise. But if you have a question, questions definitely help the seminar. And it always seems when we do these in a classroom setting, there's a couple people that ask most of the questions. However, that helps the whole group. So if you have questions, we definitely encourage you to answer or to ask them, and I will do my best to answer. Just type them in the chat. So I'll have the chat open, and then we will answer those questions, and that'll help with the seminar. So we're here in our shop. This is a typical shock bay here for those of you who have never been to CSI. We have 5 of these, so each bay has a shock dyno, computer, shock bench with vices. Our oil we use Z-Max products for suspension clean, nitrogen, and then you kind of can't see their toolbox and work area over here. So wanted to do this out here in the shop so I could show as much of the items as we can as we're going through this. So this is a seminar that I've done for 4 or 5 years, and typically we do it in a classroom setting. We've done them kind of all over the country, done several of them here, did one at Clausen Marshall Racing, and it's been very beneficial to the people. We've gotten a lot of great feedback from it, and so we're glad that you guys were able to join. We wanted to do this with all the downtime that everybody has right now. We wanted to get this going to make sure that when we do get back to racing, which is going to be soon, hopefully, everyone has a little more knowledge and feels more comfortable with what's going on inside a shock, how it works in harmony with your springs and torsion bars. And so that's the main goal today. So for those of you who don't know me, my name is Garrett Andrews. I started competition suspension in 2009. Prior to that, sorry, I'm still letting people in. Prior to that, I grew up racing on the West Coast, raced my whole childhood, and moved to Indiana to pursue a career in motorsports. And once my dream of being a driver had ended, I always loved the Indy 500 as a kid. So I wanted to figure out, how do I end up participating in the Indy 500? When I moved back here, I was a crew chief for a USAC team. And that's when I started my love for shocks. I started tuning some Penske shocks at that time, USAC had a lot of pavement races. And so we did a lot of tuning on the Penske stuff for midgets and sprint cars. And I still was on my quest to get to IndyCar. So shortly after I moved here, I got an opportunity to work for an IndyCar team as a mechanic. And I just hung out in the shock room every day after work, kind of the shock guys first in, last out. And I hung out in there a lot. And when the opportunity presented itself that they needed another person, I was the guy they chose. Several years later, I ran the whole shock department for that IndyCar team. And I left that team to go to NASCAR, because at that point, NASCAR was paying a lot of money to their shock techs. And so I thought, what's a new challenge? Let's check it out. And so I worked for Rusty Wallace's team as a shock specialist for a season. Didn't take me long to realize NASCAR's grueling schedule and everything they had going on wasn't as cool to me as IndyCar. So moved back to Indiana, went to work at Andretti Green, and which is now Andretti Autosport. And I was there when I started CSI kind of as a side gig. I had a passion for short track racing. That's what I grew up around. And I was starting to get burnt out on the travel as a professional race mechanic, shock engineer. The travel's brutal. So started CSI, and it's grown to what it is today. So I'll say this is not going to be a commercial for CSI, although I believe wholeheartedly in what we do here and the advantages we give our customers. This is going to be general shock information. Throughout it, obviously, I'll give some feedback on things that we do here, just because I have a lot of experience with it. But there's a lot of good shock builders out there. You just need to find who you can work with the most, and make sure you find somebody professional if it's not us, because there's a lot of people that have purchased a shock dyno and now they're a shock expert. I've been building shocks for over 15 years and I still learn stuff on a regular basis. What seems a pretty simple device, there's a lot of complexity in it, and there's a lot of technology that's always evolving, and that's why I continue to do Indy. Been blessed to participate in 12 Indy 500s, and I've done the last 7 years with Dreyer Reinbold. So that technology will slowly trickle down to short track racing, and that's why I'm still actively doing stuff in IndyCar on the side, because that information is going to help us at CSI long term. Now, some of that technology may never trickle down from a cost standpoint, but point is we're always learning. So my goal at the end of the day is that everybody has a better understanding of this device, how it works with your race car, what's going on inside of it, how to read your shock dyno sheets, how this works in harmony with your springs or torsion bars, and all of that. So a lot of people look at this as a black magic. There's something crazy going on in here and they're intimidated by it. It's really not, and we can break it down for the end user to make it fairly simplistic, where you're going to understand the shock and how it's going to help your race program, okay? There is no perfect setup, and so you're not going to get that today, I'm sorry. but you're going to learn a lot, and in racing there's no shortcuts. The guy who works the hardest typically has the most success. I've seen plenty of examples where a guy spends a bunch of money but doesn't put the effort in, and he's not as successful as a lower budgeted team. So you guys have taken a step today to do something that not all your competitors are doing, and so it's awesome that you're going to learn more about shocks today. So if anybody has questions, fire into the chat. Colin Davies, I'm glad you're here. It is 2 a.m. in Australia and he's tuned in. So I'll try to keep you entertained. I had a couple cups of coffee this morning, so I should be pretty good. Okay, so this shock, what is the main function of a shock absorber? Okay, so the main function of the shock absorber is it's going to dampen both the sprung and unsprung masses of the race car. The sprung mass being the body and the chassis and everything that is supported by the springs or torsion bar. The unsprung mass is composed of all the components not supported by the springs, okay? So the tire has a little bit of dampening characteristic to it in the sidewall. The tire can act like a spring, but for the most part, your shock is going to control that whole system, okay? Typically, shock tuners will refer to a shock as a timing device, because what it's doing is it's timing the acceleration and deceleration of the car, the pitch and heave, body roll. The shock is doing the majority of that, allowing when the car is going to roll, how fast it's going to roll. So a shock is a fine-tuning device. You'll never have a shock take a terrible setup and make it good. It won't happen. But you can have a great setup ruined by a bad shock, okay? A shock can't make up for a deficiency in your setup. I think there in the text, I gave the example, if you hit the racetrack and you have a track that's fast and hooked up and you probably should have 10 pounds of air in your right rear tire and you only have 4 or 5, the car is gonna bounce, and somebody in the pit stands might think, gosh, that thing has a bad torsion bar or it needs a stiffer shock, when in reality, there was a deficiency in your setup and the shock was not designed to overcome that deficiency. If it was, it wouldn't work properly when your setup was right. So again, until you have a good baseline, the shock's not really going to help you. You got to have a good platform and a good baseline. Does all that make sense to everybody? Again, if you have a question, please just type it in the chat. So the first thing I want to show you guys is the phases and movements of a shock. And we're going to, probably the nuts and bolts of what a lot of people tuned in for is how to read the dyno sheet and things like that. And we'll get to all that. But the first thing in understanding a shock is understanding the phases and movements of a shock. So this is a typical deflective disc shock. And what that means is we have a series of discs, or shims as we call them. See if I can get these off without dropping them. On either side, the rebound side of the piston or the compression side, you have these discs or shims. And this is the pyramid stack, what we call a pyramid stack. So the sealing shim is the biggest outside diameter shim. That's up against the piston, which is closing the piston off so it seals. And then the diameters, outside diameters, get smaller as it gets farther away from the piston. So those shims open and close as fluid flows through the piston. So as the shock starts to go into the compression phase, which you'll see that little diagram in your, let me see if I can pull it up here. So you guys should be seeing that now. So maybe not, now you will. So as you're seeing that first compression phase, basically what's happening is fluid is flowing through the piston and opening the compression shims. So fluid's flowing through the piston and opening the compression shims. The exception to that is bleed. And so bleed is done in one of two ways. It's either drilled through the piston, a little bitty hole, or it's a shim. And at low velocities, the fluid can bypass opening the shims and bypass through that bleed hole. Once the shock speeds up to a certain velocity, fluid can physically no longer flow through those holes, and that chokes off, and then it has to open the shims. Okay, so that is the first phase. So those shims open. When it goes to change directions to rebound, the compression shims close, and then the fluid does exactly the opposite, flows through the piston to the rebound phase. Does that make sense to everybody, kind of how that transpires there? So when we dyno a shock, we use a lot of Rohrig shock dynos here. We also have a CTW. But when we dyno the shock, it measures all those phases of the shocks going through. And it basically breaks those down as CO, which is compression open, CC is compression closed, RO rebound open, RC rebound closed. And so what that is CO, or compression open. We can also call that compression accelerating. So that's when the shock is accelerating up in compression and then decelerating down to change directions for rebound. And so the example I'll give there is, if you had a potentiometer on your car and you were measuring shock velocity, it is always moving for the most part. And if it's going 10 inches per second in the compression direction, it has to stop to 0 to go to the rebound. It can't just make that turn. It has to stop and then change directions. And so the shock is always working through those 4 phases. Compression's accelerating, then decelerating to rebound, and that happens very fast. So these shims are opening and closing very quickly. And some of you have probably sent a shock in to get repaired at one point and said, oh yeah, it had a bent shim. Well, how can that happen? Well, at some point, the fluid flowed through that port so quick that it reached beyond the yield point of that shim and it bent it permanently, so it will never sit back down and seal on the piston. And then what happens is, as that shim's not sealing on the piston, now you have an excess amount of bleed. It's bleeding through the piston before opening the shims. Your dampening is much, much softer. Typically, you're only going to see that in an instance where something out of the ordinary happened. The car bicycled up and landed back on its wheels. It maybe was in an accident, flipped and landed back on its wheels. Maybe the thing did a big giant wheelie and slammed down. It has to see a huge displacement and velocity at once in order to bend those shims. These are fairly robust. One other thing that I glazed over earlier that I want to touch on before we move forward is this shock and how it's different than a spring or a torsion bar is there's actually no force generated when it's compressed. So that shock's compressed a fair bit, and currently it's generating 0 force, okay? The exception would be if you had 100 PSI in it or a lot of gas pressure, that shaft would be coming back out. There's some built up rod pressure or spring rate internally in the shock. We'll talk about that later. But right now, I mean, we're less than a pound, okay? The seal drag in the shock is keeping it from extending. There's a little bit of internal force, but very, very, very little. So in that aspect, this works like a dynamic spring. This shock is compressed, it's generating no force. So as your car is sitting there on your setup table or at the racetrack, the shock is not adding any force to the equation, okay? It's just sitting there, has no force, very little, unmeasurable. Where a spring, if the spring was compressed, this is a 125-pound hypercoil spring, as the spring is compressed, it's generating force. So a 125 spring, the way hypercoil measures them, every 1 inch of displacement, it's 125 pounds. So at 1 inch, it's 125. At 2 inch, it's 250. It's fairly linear, okay? So as this is compressed, it generates a force. Same with your torsion bar. As it's twisted, it generates a force. Where a shock only generates a force with velocity. So as I'm moving it, it's generating a force. But just being compressed and sitting statically, there's no force there. That's important to know when you're scaling your race car and how all that works. Question from Osborne. What speed do you focus on when building a shock for a customer? 1 3-inch per second or low speed? So that's a great question. We're going to talk about that a little bit more farther in, but just to answer it quickly, we have a specific curve that we're trying to match. So whether it's a quarter midget or a sprint car, we've identified a curve that seems to work in most scenarios for that car. And so that curve, we're trying to hit certain numbers at 1, 3, 5, 6, 10, however fast we're dynoing the shock, and we have a curve that we like. Now, a lot of that curve is dictated by the piston, and we'll dive into piston technology later, but a lot of that curve is dictated by the piston. There's only so much you can do with shims to get a curve, or then it's going to come down to the flow of the piston, the shape of the sealing surface of the piston. And so we have a curve that we're trying to match, and then we're trying to hit specific dampening numbers, but the whole curve is what we're trying to match. So as a shock manufacturer, and especially a customized shock manufacturer, we've built pistons for certain applications that help us get that curve. Now, if you just were a shock tuner and you had to work with a specific scenario of parts, you can kind of only take that curve up or down with shims. You can manipulate it slightly, but unless you design a whole nother piston, you're not going to be able to change the curve. Okay, one of the things that we focus on here is we have a wide variety. I'd be sick to tell you how much inventory we have in pistons, and they're all really high tolerance billet pistons, because we found this piston works best in this scenario and this piston works best in this scenario, where some of the manufacturers, especially the lower cost shocks, they have one piston, one size fits all, and they just change the shims to get a dampening number they want, and they're not super concerned about the curve of the shock. So great question. So the next thing we'll talk about is the difference in shock design. So there's two main types of shocks used on all these markets we're in. I know a lot of you are quarter midget guys, a lot of micro guys, midget sprint cars. We have a wide variety tuned in. So there's two main differences, and you'll see in that pamphlet that I gave to you all that there's a little drawing of them, and I have some parts here to show you. So question is, how many RPM do you run your shock dyno? Do you have a variable speed motor on your dyno? So the dyno, again, that we use for the most part is a Rohrig, and then we do have a CTW as well. And so, yes, the motor is variable speed. Typically, we're going to run our pavement stuff at 6 inches per second and our dirt stuff at 10 inches per second. okay? On 2-inch stroke, everything except for quarter midget, we're running 1-inch stroke because there's barely 2 inches of stroke in that shock. So good question. Okay, so the first style of shock we're going to show you is a twin tube, and it's exactly that. There's 2 tubes. So you have your outer body, then there's an inner tube that goes in there that the piston and shaft assembly, this is a monotube shaft, so it won't fit, they ride inside this inner tube, okay? This was designed in the 60s, 70s for a passenger car. What happens is you have a gas bag that wraps around this, and upon assembly, it goes in there. That's a twin tube. Now a monotube, or a gas shock, is 1 tube. So you have your base valve, which we'll talk about a little bit later, the main body, the gas chamber, which has a divider piston in it that keeps the oil and the gas separate, and then your shaft assembly would go in there. So differences between a twin tube and a monotube. Monotubes came into play in the early 90s. It was technology from Formula One that trickled down. I believe Penske was the first to bring it to market here in the United States. The monotube shock has some real advantages over a twin tube. One, since we don't have a smaller tube in there, the size of the piston is much larger. So here is a piston for a monotube shock, and here's a piston for a twin tube. You can see they're much smaller. Okay, so we're able to flow more fluid through that piston and control it better with shims. The next big advantage is a monotube shock cools much quicker. Okay, it cools much quicker because the majority of the oil is right out here against the outer body. That's where your piston and shims are, and that's right where the air is going to touch it. So it can dissipate the heat much better. Where a twin tube shock, it's got this gas bag between it. It has a steel tube inside, which generally gets a little hotter. The internal pressures can be a little bit higher because of the size piston. And so a twin tube shock doesn't cool quite as well. The largest advantage with a monotube shock is we're able to control how much pressure is in that shock. And we do that with adding or removing nitrogen from the shock. So we're able to control, thought I was losing something, how much pressure is in that shock. Where the twin tube, it has this gas bag, and it's filled with a specific amount of nitrogen. We fill ours with 3 psi, and that's it. You can't add or remove nitrogen from that. Twin tube shocks have came a long way. From when we first started, I wasn't super experienced with twin tubes. All the IndyCar and NASCAR stuff I'd done was all monotube. And when we first started, the twin tubes on the market at that point, cast pistons, they weren't using deflective disc design, they were using a bypass spring. It was basically a passenger car shock, and all the parts were from a passenger car, and they stuffed it in a nice aluminum body. The gas bags weren't made of a nice material. We would see a lot of gas bag failures. Now, most all the twin tubes are deflective disc design. The gas bags are much more robust. And so the twin tube shock of today is much better than it was 10 years ago, a lot better. And so if you're a twin tube guy, that's okay. There's some areas where we would run a twin tube shock. A twin tube shock, as I'll show you, has some advantages as far as mounting because of the body. So a 6-inch shock on a twin tube is going to be a much shorter body. Will have a little more travel because we don't have the gas chamber. And so when I say 6-inch, another little thing to touch on, pretty much everybody in the industry, they're measuring the available stroke. So this is a 5-inch. So it should have roughly 5 inches of stroke. Now, a 5-inch twin tube is only going to have an extended length from about here. It's almost an inch shorter because it doesn't have the gas chamber. So there's certain scenarios where the twin tube mounts a little bit nicer. There's race cars like a junior sprint, light little race car, coil springs on it. We can't quite fit a gas shock with the coil springs that are on the market. They don't make a 6-inch spring that's soft enough. And the twin tubes work fine because they're not seeing massive shock velocities. Another area where you still see a lot of twin tube shocks are wing sprint cars. And one of the reasons for that is the wing controls the car so much, the shock velocities we're seeing are half of what we see on a non-wing car. And for that reason, you don't need all the control a gas shocks have, and a twin tube still win a lot of races. We're on a non-wing car, 95% of the field is on gas shocks because of the control. You don't want to be at a big half mile like Terre Haute and go flying into the corner in the car wallering around because you don't have enough control. Okay, a twin tube probably would provide enough control in the feature when it's smooth and slick, but early on in hot laps when it's really fast, the gas shock has much more control, and we can control that. So, question: does the big body twin tube use the same size piston as a monotube? And it does. And so that's one of the reasons that the wing sprint cars were using that large body twin tube, because that fixes some of the issue. We can flow a bunch more fluid through it. We're actually using the same size piston we use in our monotube in the large body twin tube. Another question. Can you test a shock and a spring together, and is there advantage? Yes, you can. And that's something that a lot of late model guys do. In the markets that we're in, I don't really see an advantage to it, to be honest. Those guys typically are doing it because it's a four-coil situation. They're wanting to smash everything together. Typically, they're doing it with the bump rubber to get load numbers, etc. It's not something that midget sprint car guys are going to see a benefit from. All right, so that covers those questions. So a couple things with the shock design is the twin tube shock has that gas bag, where a gas shock has, or a monotube shock has a gas chamber, and we're able to control the reaction of the shock by how much pressure we put in that chamber. Okay, so this has a little bit more tuning than a twin tube shock would. Now, one of the things that we get a lot is at full extension, when a guy goes to compress his shock, they're hearing something and they think maybe the gas bag's broke on a twin tube or something's wrong with the gas shock. And you probably can't see it, but earlier we talked about bleed in the piston, and there's just a little bitty hole in there. So typically we're going to run 25 to 35 thousandths of bleed in this shock. At very low speed, if you're just slowly compressing it, you're hearing fluid flow through that bleed system. On our quarter midget shocks, we run a bleed jet in the shaft because the pistons are so small, it's hard to drill bleed in it, and you're hearing that. We get that a lot on our through shaft shocks. It's got a check system in it, and you're hearing that bleed. So don't be concerned if you hear something inside your shock. The number one thing I tell people to check their shock is at full extension. When you slowly start to compress it, is there a dead spot? Does it have a dead spot and then catch? On a twin tube, that could be an indication that the gas bag is broke, okay? On a monotube, it could be that you have no gas in the shock. So if you put gas in the shock and it has that dead spot, we've either lost fluid somewhere or it's got a bent shim. So that's the best way to check. At full extension, that initial compression, is there an issue there? Do you feel a dead spot and then it catches? Okay. Again, if you've got questions, type them and we will be happy to get you answer your question. Make sure I'm not missing nothing here. I got sidetracked answering questions. Okay, so just to circle back on that, two different styles of shocks: monotube, or what some people refer to as a gas shock, and then twin tube shocks. We manufacture both for a reason. because there's certain people that don't want to deal with the gas pressure. They just want to roll the car off the trailer and race, and that's fine. A twin tube shock is much more simplistic in that aspect. There's times where a twin tube shock just fits better on the car than a gas shock. But for the most part, we're recommending gas shocks to our customers. At the higher level guys, that's what they're running. Like I say, the one exception is wing sprint cars. We're still seeing a lot of success with the twin tube, and we have a really nice double adjustable twin tube that we like on the wing sprint cars. So the next thing, before we learn how to read our shock graph, is understanding cavitation or hysteresis in your shock, and why, if you have a gas shock, it is so important to have pressure in it, okay? In a twin tube shock, as I showed you earlier, the pressure's in that bag, it's set. You don't need to fool with it. But in a gas shock, you definitely need to have gas pressure in it. A question we get a lot is, hey, my shock dyno sheet said gas force removed. Does that mean I don't have to run the gas? Yes, you do. That's just terminology that Rorid puts on the sheet to show that we did a gas test as part of our data collection. So you're always going to have to run gas in a shock. We've had people say, oh, my buddy said when it gets slick, just take all the gas out. That's definitely not the case with our shocks, and not the case with the majority of the shocks on the market. The few exceptions would be is if there's a spring behind the divider piston, and that's what's offering the pressure. So like with our JR4 quarter midget shock, we run this wave spring behind the divider piston. So quarter midget people were not wanting to fool with gas pressure. Oftentimes they're running 3, 4, 5 cars at an event. Man, we don't have time to set all the gas pressure. So we were finding that folks were going years without checking their gas pressure, and the shock was being ran without gas, which is not good. So when we redesigned our quarter midget shock, we said, we're just going to put a spring in there. That way it's set and nobody has to fool with it. I know at one point ARS had some type of spring or rubber in their shock, a line of shocks where you didn't have to run pressure. And I believe VRP was the same way. But pretty much everything else, you have to run a minimum amount of gas pressure. In just a second, I'm going to show you a video of what happens inside the shock if you are not running pressure, okay? And what that minimum pressure is really determined by the base valve build of your shock and what the dampening force of your shock is. So you'll see in the handout that I gave everybody, the same shock, one dynoed with no pressure, and then one dynoed with gas pressure. And you can see the difference between the rebound open and close and the compression open and close is very big. And what that is it's an uneven pressure across the face of the piston, and it's generating a bunch of air into the shock. It's basically breaking apart the oil into air. So I'm going to show you that video, but there's a couple questions to answer first. How should a shock be mounted? Is there an advantage one way or the other? So there's a slight difference in unsprung weight. However, it's not a large enough difference to make a hill of beans one way or the other. So I tell our customers, if you're running cockpit cables, mount the shock where you can get the cables routed the cleanest. That way you have a nice positive adjustment on your shock adjuster cable. Otherwise, mount it away from the heat. So on the left rear of midgets and sprint cars, fair bit of rebound in those shocks, so they generate a lot of heat anyway, and then the exhaust blowing straight on them, especially if you're running a place where they have mufflers. We've had some shocks come back and they've gotten so hot it's actually discolored the anodize, and that causes havoc on the oil in the shock and everything else. So try to mount them away from the heat as best possible, as best you can. So if you're in that scenario, I'd rather have the shaft getting warm than the whole body of the shock with all the oil. Question is, only ran twin tube shocks on his wing sprint car. What would he feel with gas shock? So with a gas shock, you're going to feel a lot more control. So when you go to bang into the cushion, the car is not going to move around as much. Okay, it's just going to have a more stable platform. And in my opinion, you can make just as much grip with a monotube shock if your base valve is pressure balanced right, and you have the right piston in the shock. I think you can make just as much grip and you have more control without a doubt, okay? Gas shocks got a little bit of a bad name when they first came into the dirt market in the 90s. They didn't have base valves. And so without a base valve, which isn't as big of a deal on a 3,000 pound stock car, you had to run a really high internal pressure in that shock to keep it from cavitating. And I am going to get to that video. So what that meant was you didn't have this base valve. And what the base valve does is as the main piston goes up in the shock, the fluid has to flow through the base valve before it gets to the divider piston. So it's reducing the force on that divider piston. And why that is important is if you don't have a base valve, and as the main piston's going up, it's just putting all the force against that divider piston. If the main piston moves faster than the divider piston, now we have a volume change in the shock. And there's a bunch of air in there. And then as the shock changes directions, it breaks that air into a million pieces. With the base valve, typically you're going to be able to get down to 20 to 50 pounds, depending on the build, where without a base valve, you might have to run 200 pounds in the shock to keep it from cavitating at certain velocities. So gas shocks have come a long way as well with base valve technology and being able to run lower gas pressure. How effective is gas pressure for tuning? It's pretty, so as I mentioned earlier, shocks are a fine tuning device, okay? So I tell people on a scale of 1 to 10, 1 being a unnoticeable change and 10 being a totally different race car, gas pressure is a 3, okay? It's a pretty small change, but it can definitely help. We tend to adjust gas pressure when track conditions change, or we're trying to, on pavement, maybe change the characteristic of the car. If we're just lacking rear grip, we might go down on gas pressure, get closer to the minimum pressure to take some of that internal force out of the shock and give us more overall grip. But it's I would say a 3 out of 10 on a scale of nothing to a major change. I think I explained the base valve. It's useful all the time. I would always build a shock with the base valve. Most everybody in the market does now. And I can't think of a scenario where the base valve would hurt you on our main core markets. There's some markets where guys run emulsion shocks, which has no divider piston. It's just oil mixed up with or nitrogen mixed up with the oil. There's different styles of shocks that we don't see in our market and you would see in off-road and motocross. But for our markets, I would always run a base valve shock if you're doing monotube. And while we're there, every twin tube shock has a base valve too. So at one end of this tube, this is what our twin tube base valve would look like. Little billet piston, again, fluid would flow through an open shims. Same as it does, this is our gas base valve. Shims go on this side of it and fluid flows through shims. So, what's our recommendation on changing the oil in the shocks? 20 to 25 races in the shock should be rebuilt. And the best analogy I can give you for that is it's a piston moving up and down in a cylinder with oil, just like your engine. You can only do that action so many times before the oil will break down. We use a very high-end synthetic oil, but it still needs replaced. We run as low a drag seal as possible on the shock. And so what that means, if you race in a place that's dusty or sandy, you're gonna get some of that inside the shock over time. If we sealed that perfectly, the shock wouldn't perform at its peak. So that's a fine balance there of running as low a drag of steel as you can so the shock performs the best without leaking oil or ingesting too much dirt. A passenger car, it's got 5-6 times the amount of seal drag as a racing shock because they're trying to seal that thing for 100,000 miles. Okay, I think I got all those questions answered. I'm going to show you this little video. It's from CTW Automation, and it's a clear shock that they dyno it with little to low pressure in it, and you see the shock cavitating, and then they have a pump on it and they add pressure as the shock's running on the dyno, and you can see it clear up. So pull that up for you real quick. So right there, you can see they added the pressure and now it's cleared up. And that's low pressure. And you can see that oil with a bunch of air in it. So that's a really good example of what's going on inside that shock when it's cavitating, and you can see the results on the shock dyno. The blue graph is one with little to no oil, and the red is one with lots of oil, or lots of gas pressure. So again, the blue is low pressure, oil's cavitating, the red has an adequate amount of pressure, and what you see there is the open and closed numbers on compression and rebound are very close, and that's what you want. That's a good balanced shock. Any questions so far with any of that good stuff? Now we're going to kind of get into the meat and potatoes of reading your shock graph. So the dyno sheet you received from us is a simple force versus velocity graph, and you'll see that on the sheet that we handed out. And so on the y-axis, that is your force. You'll see a 0 line. Anything with a positive number is compression. Anything with a negative number is going to be rebound. And then on the x-axis, that's your velocity line. And you can see that shock was dynoed almost 10 inches per second. That's the average force versus velocity. So Rohrig has a math channel in their software where they basically take the open and close number and average it. And that's typically what we show our customers. So that's became the industry standard. And if you would refer back to the sheet previous where we show cavitation, you'll see 4 lines there. That's open, closed, on rebound and compression. And one of the reasons we don't give that, we certainly look at that as we're building the shock and making sure it's pressure balanced correctly and all that. But one of the reasons we don't give that to the customer is if we do that on an adjustable shock, instead of 20 lines of data, now you're going to have 80. And there's just so many lines there, it becomes very hard to read. And so we just give you the average, and that's a good place to start, okay? You'll see on that sheet that I put a little arrow where the compression is crossing over 3 inches per second, and then where the rebound is crossing over 3 inches per second. That's kind of became the industry standard number that most folks are talking about. So if you hear somebody say, I have a 85 over 100 shock, there's most of the time referring to they have a shock that's 85 pounds of compression and 100 pounds of rebound at 3 inches per second. That is what we would recommend that you look at, educate yourself with, and know what those numbers are. The 3 inch per second number. That's a great starting spot. As you get more well-versed and you know more, you'll start to look at what's the 1 inch number on compression and rebound, and maybe what's my 0 number on rebound on your left rear shock. But definitely start with the 3 inch number. That's what most people are going to talk, and that's what you should know. Okay, so you can see that sample graph I showed you. That shock looks to be about 85 pounds of compression and 85 pounds of rebound. Okay, again, any positive numbers compression, any negative number is going to be rebound. The way we present the graph is similar to everybody else in the industry. Compression on top, rebound on the bottom. The only exception to that would be ARS. They do rebound on top, compression on bottom. But again, if you just look at that y-axis, their negative numbers are on top where everybody else is on the bottom. And I believe the reason ARS does that is they started by doing Carrera shocks, and that's how Carrera did it. So that's what their customers were used to seeing. Let me get the chat pulled up here. Okay. We dyno all of our dirt stuff at 10 inches per second for the most part, and then 6 inches on pavement. We do all of our quarter midget stuff at 6. The exception for that is our large body twin tubes. And the reason for that is most of those customers were coming from a pro shock. That was kind of like the industry standard in wing sprint cars forever. And they were all dynoed at 6. And so we wanted them to be comparing apples to apples. So we dyno our large body twin tubes at 6 for the most part. So Zach's question, when gas was added to that shock on the video, it doesn't create bubbles. Correct. So as the gas pressure is added, there's now an even pressure across that piston, and it's not cavitating the oil and turning it to air bubbles, okay? So that's why you have to have pressure in your shock, because the shock does not perform properly when it's cavitating with all that air. Mark, on CSI shocks, what's the minimum pressure that should be ran? That varies based on what the compression dampening force is on the shock. So we typically give you a tuning guide when you buy a new set of shocks from us, and it has the minimum pressures. If you don't have that, shoot me an email with the serial number of the shock, and I can tell you the minimum pressure on that. Nick, when adding gas pressure, does it change most of the compression and rebound stiffness of the shock? It's basically adding internal pressure to the shock, okay? So you're adding spring rate to the shock, so it's gonna make it feel like it has a stiffer compression and less rebound, if that makes sense. What physical changes are happening in the shock when you make adjustments? So that's a great question. Most adjustable shocks are bleed adjustable, okay? Our new shock that we're gonna release, I'm not sure when with all this pandemic, but our new shock that we showed at PRI, it adjusts slightly different. But we'll start with this, which is how most everybody in the industry is. It's a bleed adjustable shock. So on the shaft bleed, and if you had a large body twin tube, there'd be a bleed adjustment in the rod guide. It works the same way. On the shaft bleed, we have a jet here. There's a needle inside this shaft, and we make that needle in a bunch of different degrees, because depending on the taper of the needle will depend on how wide your adjustment range and how incremental it is. There's an inner rod that goes up this shaft, and what it does is the needle sits on top of that. So as you screw your adjuster in, what you're doing is you're pushing the needle all the way up to that jet. And when it's all the way closed, it's full stiff, the needle is totally closing off this little bleed hole in the shaft. So no fluid can bleed by. The only bleed at that point would be whatever bleed we built into the piston, and then the main shims are gonna open. As you open this adjuster, that needle will start to fall out of that hole, and now it's allowing fluid to bleed by through the shaft before it opens the shims, therefore softening the shock. Okay, you get it all the way open, the needle's all the way out of that hole, and it's very soft in whatever direction we were adjusting, whether it be compression or rebound. And that's determined by the jet that's in here, whether we're going to adjust compression or rebound on a shaft style adjustment. The taper of the needle, if you can imagine, if you have a needle that's straight, it's going to not have a very wide range, and it's going to be very small incremental adjustments, because as you're adjusting it, it's just coming out of the hole evenly. Now, if you've got a needle that's tapered like this, as soon as it starts to come out of the hole, a bunch of fluids flowing through the V, and we're going to get a wide adjustment range. So we make a bunch of different needles. Obviously left rears, we don't need a huge adjustment. We want a small incremental adjustment. Fronts, we need a larger adjustment. So we have different tapered needles for that. Okay, so that covers that. So on your shock dyno sheet, there's two ways to tell what the dampening force of the shock is. To look at the graph, like we showed, identify whatever velocity you're wanting to dissect. I recommend 3 inches per second, and see what the compression number is in the rebound. Now you're gonna guess slightly. And what I mean by that is on that shock, you can see that it's just a little bit below 100, above 50. So we're gonna say that's maybe 85 pounds, okay? If you want the exact number of what that is, with our dyno sheet, we're gonna give you all the data as well. So you'll see a data chart that comes with it. It'll have all these columns, compression open, compression close, rebound open, rebound close. The last two is what you should focus on. That's compression average and rebound average. And if you count down to 3 inches per second, it'll tell you exactly what that is. That might be 83.24 pounds of compression and 86.17 pounds of rebound. That'll tell you exactly what it is. And that's helpful on adjustable shocks because you can see, okay, at 8 clicks open, it goes to this, etc. The exception would be quarter midget shocks. We're doing all of our quarter midget stuff on a new CTW dyno, and they don't have the math channel for averages yet. So we're sending you compression open, rebound closed, and those are the numbers you would look at. Our shock's built to meet certain chassis. And so that's gonna kind of get us, that's a great segue into our next area where we're gonna talk about the different parts of the graph. And yes, they are. Depending on who's building your stuff, us smaller manufacturers, more expensive, higher end shocks, the CSIs, the Factory Canes, the Penske's of the world, we're custom tailoring our shocks. So every single shock is built to order here, and we ask a series of questions before we build that shock. What type of chassis do you have? What tracks are you racing at? How much does your driver weigh? And that's going to help us get a really good baseline shock package for you. And then we try to stay in contact with our customers as they reach out to us and get feedback, because what works for the masses might not work for everybody. So we feel really good that when we send that set of shocks out, it's going to get you 90, 95% of the way there, maybe 100 in some instances. It might be ideal for you. But then there might need to be a little more tuning on that based on a specific driver's feedback or feel. If I look at like the USAC midget ranks where we've got a good market share, I think we had 4 of the top 5 in national points last year. They were all on a slightly different package that we've custom tailored for them. So that's one of the things we really try to do with our customers, is be very accessible. Obviously, we can't call every customer on Monday and see how they've done. But we are, myself and Jake and the guys that work here, we're very accessible, whether it be through social media, email, call us here at the shop, and we can help you tune that last little bit, whether it's an adjustment in the shock or it needs to be revalved. We want to make sure you get the most out of it. So that is why we custom build everything here at CSI. Shocks are not a one-size-fits-all answer anymore if you want to compete at the highest level. Now, certainly if you're just racing locally, you might just be able to buy a stock shock off the shelf from a speed shop and be okay. But to compete at a national level or the highest level, your shocks need to be custom built for your application. So great questions, everybody. Please keep them coming. That'll help keep this thing rolling here. Make sure I didn't miss anybody. Okay. So now the main differences here we're going to talk about in the dyno sheet is low speed and high speed. Okay, what is low speed and what is high speed? So if you look on the graph, I identify with an arrow what low speed is. And typically low speed is going to be 0 to 2 inches per second. And high speed is going to be like, 5, 6, 7 inches per second and up. And low speed is typically what the driver feels. High speed is what you would see from the stands. So the driver's feeling low speed more so than high speed because the shock spends more time there. Even if we're seeing a peak velocity of say 20 inches per second, the shock is spending the majority of its time at the low speed because every time it speeds up to that velocity, it's got to stop and change directions. So it's constantly coming back to 0 and changing directions. So the shock is spending the majority of its time right in that turnaround point of the graph from compression to rebound. And it spends a lot of time there, and that's what the driver is going to feel. So low speed typically is controlled by bleed in the piston, piston shape and design, and where high speed is going to be the preload in the piston and the shim stack more so. One of the advantages of being a smaller shock builder is we've got tons of shock, different style pistons, design pistons, and we've customized that for different applications. And that's going to help us get the curve that we want for a specific application. So you can see on that graph that the 3 inch per second number is almost identical. Okay, 3 inch compression looks to be about 70 pounds and 3 inch rebound looks to be 220-ish, 225. They're almost identical. The red graph and blue graph are almost identical, but those two shocks are going to feel drastically different. You can see the red shock has more low speed than the blue, but it has less high speed on the compression side. And then on the rebound side, it has a little less low speed and a little less high speed. Okay, so those are different curves and they're going to yield different results even though the 3 inch per second number is the same. Why is that important? Why it's important is forever people went off the generic valving number of the shock. So that nomenclature, your 3, 4, 5 numbers, those aren't a unit of measure, and we don't use those here at CSI except for our quarter midget market, and I'll explain that in a second. But anything bigger than a quarter midget, we don't use those numbers because there's such a discrepancy there in what it is. So AFCO may say a 5 valve is 75 pounds, and Penske may say it's 85, and ARS may say it's 65. None of them are wrong. That's just what they prefer to call their 5 valve shock. There's no book or anything that says a 5 needs to be this. Also with that is there's tolerancing. So your lower end shocks, the more cost-effective shocks, they have a larger tolerance because the quality of components in them are less. They're trying to build more of them an hour, so their tolerances are wider. So it might be a 5 valves anywhere from 62 to 82 pounds. So you might get one that's 62 and you might get one that's 82, two drastically different shocks. Or if you know how to read your dyno sheet, you're going to know exactly what you have. If it says 85 pounds, it's 85 pounds under those parameters it's tested. So that's really important to know. And then also, what does that manufacturer, what velocity are they looking at when they determine that valving? And it can be different based on the manufacturer. So for the most part, if you're working with the same manufacturer of shocks, their curves are going to be similar, okay, for a given market. So our non-wing sprint car stuff, the curves are all going to be pretty similar. If you get one that's 90 pounds and then one that's 85, they're going to be a little bit softer. The 85 will be a little bit softer the whole way through. The curve's going to be the same because we're using the same piston. Why we don't recommend to use different brands of shocks on different corners of the car is because the curves can vary drastically based on their piston design. So if you have a QA1 on the left front and an AFCO on the right front, one might have a very soft low speed and ramp up, and the other one might be really linear, and the shock's going to be and feel totally different, and your car's not going to be balanced, right? So if you're using one manufacturer, whatever they determine, whatever their engineers determined they wanted that dampening characteristic to be, it's going to be similar on all 4 corners, and we should have a decent balance. But if you have different brands of shocks, the car's going to be totally out of balance. Okay. So that's one of the reasons I'd recommend sticking with one brand on all four corners. Okay, so this guy has a question about different shock. He's saying RPM. What happens if you run the shock at different velocities? And we're going to explain that in just a little bit when we break down different ways to dyno your shock and how to identify that on your dyno sheet. Another question is, have we had a chance on our left rear shocks to run them to a high temperature to identify what it looks like when the shock gets really hot due to an inboard brake or a muffler, etc. This guy's on the West Coast, so they have to run big mufflers, and there's a heat issue there. Yes, we have. And we typically, as we have been experimenting with different shock oils and even testing shock oils for different companies, we want to run them up to a high temperature to see what effect we have, how much force fade we're having, because that can vary on the brand of shock oil, what additives they have in the oil, what the anti-foam characteristics look like in the oil. And typically when we get up around 300 degrees outside temperature, so these dynos have a infrared temp sensor, so we're checking the temperature on the outside of the body. Typically around 300 degrees is when we start seeing some substantial force fade. So that's with the oil that we use, and we feel it's the best oil on the market, and that's why we use it. You know, once we typically dyno the shocks at 85 degrees. So the hotter you get, the softer the shock's going to get. Again, that depends on the oil you use. So we run a very thin, probably see it, this red jug. It's very thin, right? They call it like a 2.5 weight. So the thinner the oil you use, the less fade you're going to have because the oil's not going to thin out, number one. But as that oil gets hotter and thinner, it can go through bleed passages easier and different things. So the hotter the shock gets, the more it's going to fade for sure. Over 300 degrees, we start to see a larger amount of fade. So hope that answers your question. Colin Davies, the Iron Man who's staying up in, it's probably 3 a.m. in Australia now. He asked, what do we do inside the shock to control 1-inch numbers? Typically it's bleed, Colin. Depending on the amount of bleed that's in that shock is really going to control the low speed. When we look at a shock graph, like that blue graph on the comparison there, you can see where it starts to ramp up around a little over 2 inches per second. So the shock's probably bleeding to that point. Once it gets over 2 inches per second, the velocity has increased so much that fluid physically can't flow through that hole. So at really low speeds, we got fluid bypassing through the bleed port or bleed hole. And then when the piston's moving very fast, the hole's so small, it chokes off and fluid can't flow through there, okay? When that happens, the shim's open. You can see that starting to happen around 2 inches per second on that blue graph. So low speed is pretty much solely controlled by bleed. If you have a different brand of shock rebuilt by you, can I run them at this? If I have a different brand of shock rebuilt by you, can I run them at the same time? If it's say a small body, for instance, our internals will fit in an AFCO. So if we put our base valve and piston in there, then yes, it's going to perform very similar to a stock CSI shock, and you would be able to do that. If it was, say, a Penske that we don't have it's not going to match the piston that's in our gas shock, I would say no. But AFCO is one. Our twin tube started as an AFCO, and we started making pistons and different things, and now it's a whole own CSI shock. But we stayed with that same ID 30 millimeter piston, so it'll fit in an AFCO. We blueprint a lot of AFCO quarter midget and midget and sprint car shocks with our internals. So that's one example where we can put our guts in it and make it feel the same. Does corner weight have an effect on how you build a shock? If so, how? So pavement racing, it can. Typically for the dirt world, no. How you're going to run your race car, it would have to be drastically different than the norm for us to really consider a shock valving change. For example, if a guy said, hey, I'm going to run a reverse split in the back of a sprint car, I'm not really going to build his shocks different than a guy who's running paired up or positive split. It would have to be pretty far out in left field, maybe the motion ratio of the shock changing, drastically different arm lengths or something like that where we would revalve the shock. Would you run small body and big body shocks or different velocity, viscosity oils, different corners to change the rate throughout the race and track slickness? I would not. There's a lot of guessing there. There's a lot of, you're making a lot of assumptions at that point, I feel, in my opinion. We want to run the shock style that's going to be best for that race car. And I'm going to stick with the thinnest viscosity oil I can because I want to control the dampening with the shims and the piston design and not whether the oil is getting thin or thick with heat. Okay, so that'll answer that one. Let's see back where we were at here. So with that, a couple different pistons here. With the shock graph there where we show the different low speed and high speed dampening characteristics, that's why it's important to work with a manufacturer or shock tuner that is very familiar with your application and they have the internal parts to get you the dampening curve you need for your application. Now, what I say your dampening curve needs to be might be different than another shock builder. We do it based off testing and the information we have. Obviously, we build a lot of shocks here and we get a lot of feedback from our professional teams, and that's taken us down a path where we feel is best as far as the dampening curve, and it does evolve. I would say the dampening curve we were running 3-4 years ago on a USAC sprint car is different than today. And a lot of that is evolution of what we've known and what is better in testing. And then some of it is rules changes, whether it's the tires different now, or maybe they're building the chassis now with the motors up higher, and different things change and trends change within the industry, and then we have to change as well. So bigger companies that have like a one-size-fits-all piston, you're not going to get the most performance out of it. So here is like a cast steel piston that you would find in a lower end shock, and this is like a billet piston that we would use. Most of your high-end manufacturer are using all billet pistons. Öhlins is one that still uses steel. They have, one of their engineering philosophies is they like the weight of a steel piston and how that controls the shock, but they're very nice billet steel pistons. No other questions as far as that goes. So a guy had a question earlier about shock velocities and how dynoing at different velocities will give you different results. Typically, at this point in the seminar, I would run a shock on the shock dyno. I was concerned most people wouldn't be able to see that, so I didn't prepare for that. But if you run the same exact shock at 6 inches per second and then run it at 10, the graph is going to look different. And that is due to the rate of acceleration on a crank style shock dyno. It's not that one's right or the other's wrong. It's just you're not comparing apples to apples. So it would be no different than if you had a race engine built by shock builder A, and these were the parameters he used to dyno that engine as far as fueling and air density numbers and all that, and then you took it across down to shock or engine builder B, and he dynoed it with a different set of parameters, and one said 900 horsepower and one said 850. It's not that one's right or one's wrong, it's just they were tested under different parameters. So it's very important if you're comparing different shocks. If you get them all from one builder, I'm assuming the sheets are all going to be the same. But if you got shocks from a couple different places and one's dynoed at 6 and one's dynoed at 10, you're really not comparing apples to apples. For the most part, they'll be pretty similar with the exception of a left rear. When you get into big rebound stuff, the rate of acceleration plays a huge role. Also, there's two different styles of tests that are most common on crank dynos and in our industries, and it's a CVP and a PVP. And a CVP test stands for constant velocity plot. So what that means is the shock is going to, you're going to dyno it to a specific velocity. So if we say 10 inches per second, it's just going to ramp up to 10 inches per second, collect data the whole way up and the whole way down. And then it's going to plot a graph based on the forces it saw throughout that velocity. I don't remember off the top of my head. I think Aurora collects like 200 points of data every second. So it'll be a very fluid looking graph. You can see the blue is the CVP test, and it's very fluid looking. Now that's the same shock dynoed on a PVP test, and you can see how different the graph looks. So PVP is peak velocity plot. And when you build a peak velocity plot test on the dyno, you tell it what speeds you want to dyno at. So I can see clearly we said 1 inch per second was one of them. We probably said 3, 5, and 7, and 10 were the others. So what it does is it runs the shock at 1 inch per second, and it takes a reading. Pauses, then runs at 3 inches per second, takes a reading. Then it draws a line from the 1 inch data that it took to 3, a straight line. So you can see we went from 0 to 1, and it drew a straight line down to 1. And then from 1 to 3, it drew a straight line, and so on. Well, you can see once you get out past 5 inches per second, the two tests almost overlay with each other. At low speed, it looks a lot different, and that's due to the rate of acceleration. So when we did it at 10 inches per second, it sped up so quick, it went past 1 inch per second at a different rate of acceleration than just going from 0 to 1, and that's why they look different. Again, not that one's right, one's wrong, they're just different. And if you start to really dive into your shocks and you want to know more information, you need to know what you're looking at, okay? Typically, it'll say whether it was a CVP test or a PVP. A tell-all, if it doesn't, is if it looks kind of like a dot-to-dot line, that is going to be a PVP, where a more fluid graph would be a CVP. We do CVP here, and that's just what I've learned. All of our IndyCar stuff was always CVP, and it gives us all the information that we want to look at. If you PVP, it's easy to overlook deficiencies in the shock from a pressure balance and hysteresis standpoint, because you're not looking at both sides of the graph. So we use CVP. Some builders use PVP, but to me, the shock is never just running at 1 inch per second and then running at 3 inch per second. So why would we dyno that way? It's speeding up and slowing down at all times. So a CVP test does everything we need it to do. Questions? Since each corner of the car goes through different reactions, does it make sense to have different valvings for each? In some situations it does, and in some it does not. Typically, we're different on all 4 corners, with the exception of quarter midget stuff. And a lot of that has to do with the dampening characteristics of a quarter midget shock. It's so soft. You know, a spring rate change can be the difference we need. It might necessarily doesn't have to be a dampening change in the shock. I don't think I touched on that earlier, but I was talking about traditional valving numbers. Now we still use them in the quarter midget world. And the main reason is just for simplicity. That's how every single quarter midget shock manufacturer calls out their shocks. When I first started, I tried to buck the trend in the quarter midget stuff and teach folks, and it just had everybody confused. So we ended up going about the second year of our quarter midget program. We went to a traditional valving number. I still encourage those folks to learn their 3-inch numbers. And a lot of those folks that use the Pit Logic app will get those numbers in their Pit Logic so they can see exactly what the real number is. But all right. The next thing we're going to dive into, and again, if I'm going too fast or you have a question, please type it in the chat and we'll get it taken care of. But the next thing is all the shock curve comparison. And these are kind of exaggerated examples, but it'll show you a digressive curve, a linear curve, and a progressive curve. And we use a combination of all of those here at CSI. Again, different builders have different philosophies, and not that one's right or one's wrong. Typically, like a progressive curve on the compression side is going to offer more grip because we are going to allow more roll in the car. But when the track gets fast, we need to load the tire quicker. You're going to want more of a linear curve on the compression side. On the rebound side, we're most of the time going to run a digressive curve because we want to build a lot of control into it at low speed, but then we want to blow that off. So if we did a linear shock and we built the dampening into it we needed at 1 inch per second, it would have so much rebound at 10 inches per second. If you ever hit a hole, it would hold the tire out of the track. So that's why a digressive curve is advantageous for left rear rebounds. And I would say most every manufacturer is running a digressive curve on left rear rebound. Some of the pavement stuff we run progressive. A lot of our front shocks will run linear with we run a different type of shim stack, not a pyramid stack, but a ring shim stack so we can get some low speed control and blow it off. We don't want to quite run a digressive piston because we don't need that much low speed control. So there's hybrids of each of these graphs, but that kind of explains the differences there. Our quarter midget shocks, and every shock we build, we call out compression and then rebound. And that's pretty much the industry standard with the exception of ARS. I'm not picking on them. They did Carrera shocks early in their company, and Carrera, for whatever reason, called out rebound then compression, and they stayed with that, that style moving forward. So it's a little confusing, but all of our stuff and anybody else in the industry does compression and then rebound. So good question. Are we going to cover Pit Logic? We're not going to cover Pit Logic today. We did our Monday morning quarterback on it last week. So if you want to go back and watch that, just to briefly explain Pit Logic, it's a setup app, pre-built templates in there. It's a way for you to keep all your setups right there on your phone or your tablet, have your shock data, and we just keep adding to it, right? So now we have a parts section in there where you could keep track of the laps or miles on all the key parts on your race car. There's a tire library in there where you can have all your tires in there and sort them by stagger and condition, keep track of information on your tires. The gear chart thing where we can help you select gears based on the data you input. There's a fuel consumption built into the setups. There's just so much there. It's a very, very handy tool, and it's Mike, if you have a question on it, right now, as we did this latest update, we switched it to a free download for 14 days. So just download it. It doesn't ask for your credit card or anything. Download it. The Pit Logic YouTube channel or the website has a bunch of little 30-second to 1-minute videos on how to do some of the features in there. There's also a really nice tutorial at the bottom. So if you've never fooled with it, download it. It's free. Go through it and see if it's something that you would like and you can benefit from it. But we have hundreds of people on the platform, and all the feedback we get from those folks, we keep adding more and more features to the app. So it's certainly helpful for my program, and I think it would be for yours as well. We do have a pavement sprint car template in there you would download and then put your stuff in, and now the templates are really customizable. If there's certain things in our setup template you don't want to record, you can get rid of those and add things you want to record. So would it make sense to change shock valvings on different quarter midget tracks, or even different valvings as the day or track changes? Great question. I obviously have access to all the shocks I could ever want and dream of. And in my testing with our house car program that we've ran for several years, there's other things you can do to tune your race car that are easier to do throughout the day than changing shock valving. So certainly if you go from a flat parking lot to a place like Kalamazoo or Orange Show that's banked a lot, we're going to change our shock valving a little bit. However, as track temperatures change or the level of grip changes in the track, we've found that ride height adjustments, stagger adjustments, cross weight adjustments, weight bias front to rear are just as positive, if not more positive, than a shock valving change, and they're much easier to do than changing a shock and rescaling out the car. So again, I have access to every shock a guy could ever want, and typically I'm not adjusting shock valvings at the track unless I'm really out in left field and lost. But for the most part, we've got a good baseline for all the different chassis and flat tracks, medium bank, high bank. And once we roll to the track with that shock valving, we rarely change it. I rarely change springs as well. I tune the car dynamically with chassis adjustments. Sometimes I'll do a spring change. I'll do a spring change more frequently than a shock change. But no, we don't make a ton of valving changes for the same track, just because it's a process to change your shock and rescale the car and all that, and it's not as powerful a change as some of the other things that you see. So, does adjusting monotube pressure require even small adjustments to the compression rebound to offset this? No, and what you're doing is you're adding internal pressure to the shock. And so typically if the track's fast, we're going to run more pressure. If the track's slow, we're going to run less pressure. And we don't make valving adjustments externally on the adjuster knob to compensate for the pressure we did. So we're kind of changing two different things. It's like we're adding spring rate to the car with gas pressure. So typically we don't make that adjustment. So that covers pretty much all the shock stuff we were going to cover today. I'll graze over the torsion bar stuff. Again, if we were in a classroom setting, we would run a bar on the dyno and show you that. There's a bit of information in that torsion bar stuff to look at. The one thing I would want to touch on torsion bars is the bar typically does not get softer as it wears out or gets old. It actually can, most instances it'll get stiffer, but what happens is it starts to slow down on the rebound side. So it's not reacting as quick. When the bar winds up and then it releases back, it's not doing that action as quick. And so identify on the bar graph there where we can check the turnaround point of the bar and where it's starting to slow down. So when the compression rate of the bar and the rebound rate start to get farther apart, that's when the bar is not good any longer. And we recommend 20, 25 races for a sprint car guy, and they should be putting new bars in. So we dyno bars all the time here. If you had a question on a bar, we can certainly dyno it for you, or there's people throughout the country who can dyno it. One thing I will touch on is just make sure whoever's dynoing your bar is the person who's doing it all the time, because there's a couple different machines on the market and they give drastically different rates. Again, not one's right or one's wrong, just based on the length of the arm they're testing with, based on the torsional rigidity of the machine, they give totally different results. So if you buy new bars from us and they come with a dyno sheet, and then your local guy has, we use a Maxwell bar dyno, and your local guy has a, I don't know, AccuForce bar dyno, the rates are going to be totally different. You're not going to be able to compare them. So don't try to do that. Do you use load sticks to rate bars on the car or just off the car? So we're not really, the load sticks are kind of a new thing. If I was pavement racing, I could see where the load sticks could be beneficial to basically get all my loads where I want. And then if I do a spring change, get back to that same load. We do a version of that in IndyCar. We have a machine that we compress the shock and the spring to a specific extended eye length. And then when we do a spring change, so we have a certain number we're trying to hit, and we do a spring change, we compress it, and we'll adjust the ride height adjuster till we get that load. Load stick's doing something very similar. So for pavement racing, I can see that being beneficial. I don't know that I haven't fooled with it enough on dirt to say whether it's worth your time or not. My gut tells me it's probably not. It's just one more thing to complicate the matter. You know, simply blocking the car is probably going to be enough for dirt and staying on top of all that. So the next thing that we had in here was kind of bump rubber technology. Again, we would typically show that on the dyno. We have our progressive kit that has worked very, very well for us. The only downfall to it has been on some of the micro stuff, we're not able to get a short enough bump package. So for that progressive kit to work really well, it's about 3 inches tall. And on a lot of the micros, we just don't have enough travel. So we've been exploring options and trying to come up with a way to have a better bump rubber than just a foam rubber in the cup like a lot of folks use and we sell. We're trying to get something like the progressive kit in a shorter package, and we tried a bunch of different things, and iBlock reached out to us that they had something they wanted us to try, and it's this bump spring. And a lot of the bump springs that we've seen in the market, I wasn't a huge fan of because the target you're shooting at is fairly small. This is a much softer spring, but the way it's built, we're getting the rate we need and the travel we need. So this is something we're going to start fooling with once we can get back on track. We did a little bit of testing with it before, but it comes with a nice cup with an O-ring seal based on the shock shaft you have. If you want to know more about that, Monday Morning Quarterback this week is going to be about bump springs. It's something we haven't been a big proponent of in the past, but the advantage of it is the short installed height is going to give us some more flexibility. So we're going to show you why we prefer this one over some of the other ones on the market. And again, it's not ours. It's an iBlock piece. We sell it, but it's the nicest bump spring setup I've ever seen. Very consistent rates and the curve we want. So that kind of covers everything we were going to go through today. But I'll hang on here and answer any questions you have. So if you have a question, fire it in the chat. If you don't have a question, we hope you all have a good afternoon. Thank you so much for tuning in. If there's ever any questions I can answer, feel free to call the shop, shoot me a message on Facebook, or you can email Garrett at csishocks.com. Always happy to answer any question I can for you, and appreciate you spending part of your Saturday with me. So like I say, I'll hang out for a couple minutes to see if anybody has any questions. And if they do, I'll happily answer those. And if I miss your question, again, just reach out to me and I'll get it answered. We do Monday Morning Quarterback every Monday, and it's usually a 20-minute program. We do it at 9 o'clock Eastern on our Facebook Live. And we typically have a topic that we cover, and then we answer any questions. So that's another good way to get a hold of us. If you're not a Facebooker, all of those are on our YouTube page. So you can subscribe to our YouTube page, and I try to post those each week, or sometimes I'll get a couple weeks behind and post multiple, but all 93 episodes are on our YouTube page if you want to go back and look. And the title of it gives a good explanation of what we cover that week. So On a wingless sprint car, what corners would you bump? So wingless dirt, typically we do the right rear, although Mike is a pavement guy, so I'm assuming that's what he's talking to. You know, on pavement, we've seen, we've went both ways. We've ran bump rubbers on the front, and it seems as of late, bump rubbers on the rear are what is working the best. To be completely honest, we don't get to do as much pavement racing as we like with sprint cars anymore. Most of the time, 90% of our pavement racing is combined into a couple weeks there at the Little 500 at Anderson, which maybe isn't the best place to test because it's higher bank. But we've been running rear bump rubbers there with a lot of success, and that's been a good thing for us. So I think you can do fronts or rears. I don't know that you ever want to bump all four, but probably depends on the track some too. I know pavement midgets for a long time, like at Irwindale, we got to where we were running softer front springs and bump rubbers, and it really helped the car get down to the flat and turn on the bottom there. Where Anderson so banked, the car turned so well, front bumps weren't where it was at. So. The Eibach isn't available for quarter midgets. It'd be way too stiff. Our progressive kit for the quarter midgets is where it's at. We spent a bunch of time developing that, and that's a nice soft rate for quarter midgets. That's definitely what I would recommend. If it's legal where you're at. USAC bump rubbers have been outlawed, but QMA, they are legal. Make sure I'm not missing anybody. Can we go over how the rebound adjuster in the gland works on the big body twin tube? So it basically works the same as the shaft. I don't have one here to show you, but as you adjust, the needle goes up and plugs off. So basically on the rebound side of that tube, we are adjusting bleed. So it's allowing fluid to bleed by. There's a needle inside that housing, and we have different tapered needles based on what shock is we're building. Yep, all the thank yous, no problem. Glad I could do it. Are there general rules for a bigger driver? Typically, the right rear needs to be stiffer for a large driver. I'm a bigger guy in racing. I wish I would have known what I knew now when I raced. But typically, the front shocks don't need to be changed much because most of that added bias is towards the rear. Right rear dampening, we're going to need to be stiffer on compression to have more control because your upper body weight's so high. So if that's an issue you're experiencing, you feel like maybe you're getting way too much travel or too much roll on the right rear, get with me and we can see about revalving your right rear for a larger driver. Yes, we've ran the bump rubbers on the left front to help control down travel. And we've also ran them on the right front at certain short tracks where it's really banked and we're not wanting the car to dip over on the right front. So we've ran them in a couple different scenarios on a wing car. Pretty much always run them on the left rear, but there's certain instances where they work on the front as well. Our progressive kit, we have some Mark Smith, who's a really, really good Wing 360 guy. He's a dealer for ours, builds Mach 1 chassis. He runs the progressive kit across the back. And I think he typically would have his gap opened up where he's not really getting in the right rear until the track slicks off. And then when he slides the wing back, it's sitting on those bump rubbers on the back. And he wins a lot of races running them across the back. So I think if you get them timed right, it can really help with controlling the attitude of the car and rear grip. Brandon, you've ran the progressive kit on the right rear of your micro, and should you go to the cup style? So the progressive kit isn't designed to be ran in a cup. If you have enough travel, I still think the progressive kit is the way to go. But it's 3 inches tall with 3 pucks, which is about how we like to run it to get the rate we want. And so you really need like 4 inches of travel on your shock. So you have an inch before you get into it. 1.5 inches before it starts to build rate. So if you have that much room, I think you're good. I would stick with it. I know with your new hyper, you should have close to that much room, if not more. We've ran into issues with a lot of the Jacob's ladder style cars that run the shorter shocks. We just didn't have enough travel, and that's where we're going to be working with this new Eibach bump spring. So. Gabe, you missed the first part of it. I'm not going to make any promises because I'm not super tech savvy, but I'm pretty sure this recorded the whole seminar. And if it did, I will upload the whole thing to our YouTube page. So I'll make a post on social media once this is done, and we'll try to get it all uploaded to our YouTube page. As long as I didn't do anything wrong, that was the intention, was to post it so where people missed. I saw I got a bunch of emails in the first 15 minutes of people wanting to get in, and I just didn't want to stop the seminar and send invites and whatnot. So we tried to give everybody an adequate time to get in and whatnot. But Aaron, where can you find more information about bump springs, particular application? Again, we have some great Monday morning quarterbacks where all we do is bump rubbers. It's a two-part deal. I can't remember what the episode numbers were, but if you go to our YouTube page, there's 2 episodes just on bump rubbers, and we're going to do one Monday on bump springs. And then again, if those don't answer your question, just reach out to me and I'll help you as best I can. Cameron, what's the advantage of running a bump rubber or spring on the left front of a wing sprint car? So in a wing sprint car, the amount of travel on the left front is a huge tuning tool for the car. So it'll pretty much take everything you give it. So if you give it 5 inches, it's going to travel down so far on the left front that it's going to get the right rear out of the track and make the car loose. So we try to control how much down travel we give the left front. On a short track with a 410, typically like 3¼ inches, we'll let it travel down 3¼ inches, and that seems to be enough to get the left front down to help it turn without getting the right rear out of the track. On a half mile where we got a lot of wing speed, we're going to do less left front travel. Typically like 2¾ is where we would start. If we gave it more, it's going to travel down so hard on the left front, it's going to get the right rear loose. So the bump rubber we can use to get that gap rather than just packers or different height rod ends where it's just an abrupt stop. Some guys like the bump rubber where they can feel it, get down to it, and on a bump rubber rather than an abrupt stop. Do I feel a person would see a difference in torsion bar numbers at the end of the race versus the beginning? No, typically a bump rubber, a torsion bar. Is that what that said? Yeah, we see a difference in torsion bar rate from the beginning of the race to the end. I don't believe so. We've ran the heck out of bars on the bar dyno, and they're not very affected by heat. And if you have a good quality bar, it should be the same from the beginning to the end. That should not be an issue. Would we ever recommend a compression adjustable on the right side when rules only allow for a single adjustable shock? Sure. We run a compression adjustable right rear a lot on non-wing sprint cars. So I think there's definitely a time and a place for it. We were compression adjustable right rear on our micro package for a long time. And just here in the last 1.5 years, we went to a different piston and a rebound adjustable right rear. So yeah, certainly there's an instance where compression adjustable would be beneficial. Would a bump in the left front help the car in the center of the corner? It could if you're trying to get it back to the right rear quicker. You could control that by the center of the corner on pavement where you're seeing the highest load. It gets into that bump rubber and helps transfer back to the right rear. If you're lacking maybe side bite from the center to exit. What would you change on your monotube package when switching from wing to non-wing micro? So typically we're going to run less front rebound on a micro when we take the wing off. If you had a non-wing specific package, we would run a little bit more left rear compression. So you could do that by maybe going up a little bit on gas pressure on the left rear and again, less front rebound. So typically the right rear will be similar. We're going to be 25% I would say less rebound in the front shocks for non-wing, and maybe 10 pounds more gas in the left rear shock. Is our progressive kit the same as the Apollo bumps on the RE website? They are not. So we did the progressive kit with RE suspension, great friends of ours. Jason Enders is a super dude and really, really switched on. They basically do what we do in stock car racing. And so when we wanted to do the bump rubber stuff, I reached out to Jason because they do way more of it than we do in stock cars. I believe their Apollo bumps are a little bit different. So we have some different rates and different washers, but we have, if you shoot me an email, I can send you the graphs. When you buy a kit, it comes with the graphs, and I just don't know if we haven't posted on our website, but I can get you that information. I think the Apollo kit is different on RE's website. When running on a smooth, slick track, can reducing gas pressure provide similar benefits to a twin tube? Absolutely. So as the track slicks off, slows down, decreasing gas pressure is going to slow the shock down and make it feel more like a twin tube. So my example earlier was this shock. I don't know how much gas is in it. It's a left front. It acts like a twin tube, right? Like that shaft is not moving back out. So it has a low enough pressure that the shaft isn't moving back out. So if you, when you get your gas pressure back down, it's going to act like a twin tube for sure. Currently don't run bump rubbers on a micro. Would it be beneficial to start running them? So micros, you get a little bit of a mixed bag because they run everything from like purpose-built micro tracks that are smaller, like 1/6 and 1/8 miles to like 3/8 miles. If you're running on a really big track, I definitely think you can benefit from a bump rubber in the left rear. If you're running non-wing micros, I think you can benefit from a bump in the right rear. But what I tell our micro customers is make sure you have a really good baseline. Once you feel really good about your baseline, you're comfortable in your adjustments, you feel like the car is pretty good, and you're wanting just to get a little bit more, let's start experimenting with a bump rubber. And depending on what you're doing and what tracks you're racing, will give you a recommendation on a good starting spot for that. Yep, no problem. Happy to share anytime I can. So it doesn't look like any more questions. We hope you guys have a great rest of your weekend. Again, I will try to get this posted to our YouTube for those of you who missed it. And thank you all for participating and asking questions. Hope you stay healthy and our country gets through this quickly so we can get back to racing. I certainly miss being at the racetrack and seeing y'all. So have a great day and thanks again.